All right, I think you can get started now. Please take a seat. So, good morning, everybody. My name is Julien. I'm a tech evangelist with AWS. I've been working with them for almost 3 years now. And these days, I focus on AI and machine learning. And it's really nice to be back in Krakow. I was here for Code Europe in December. It was cold and dark, very cold and very dark. It's very nice to enjoy the city with sunlight and getting a chance to visit. It's really beautiful. So, good to be back. So, my topic today is deep learning for developers. And, well, the title is really important because it means if you can read and write, let's say, 50 lines of Python, you can do this, okay? So, we're going to start with an introduction to the underlying concept, some of the theory that actually holds deep learning together, but I'm going to try to make it as pragmatic and concrete as possible with minimal theory. And then we'll look at some code, run some examples, and try to put everything together, okay? So you've heard of deep learning as a subset of machine learning that uses a technology called neural networks, right? So the first thing we should look at, and I realize this is really hard to start with this slide, but hey, we got to understand what this thing is all about, right? So stay with me here. We got to understand what a neuron is. And what we're trying to do really is trying to build some kind of approximation of a biological neuron. So what we know about biological neurons is they have inputs, they have connections, and if those inputs are stimulated enough, then the neuron will actually fire. It will emit an electrical current. If it's not stimulated enough, it won't fire. Okay, so we're trying to build something that looks a bit like that. So obviously, for a deep learning neuron, we will have inputs, okay, and these will be floating point values. We'll see where those come from. And to each of these inputs is associated a weight, which is another floating point value. And this weight, in a way, makes this input more or less important than others, okay? And the first thing that we do when we actually run something on that neuron is to compute this multiply and accumulate operation. So we take each input, we multiply it by the corresponding weight, and we add everything together. Okay? It's called multiply and accumulate. So there you go, right? Deep learning is really about adding and multiplying stuff and doing this at very large scale. So if you can add and multiply, you already know 50% of what deep learning really is, okay? But the problem with this function is that it's a linear function. If we change the inputs, right, if the inputs vary linearly, then the result, that u value, also varies linearly. And that's not what we want, because remember, we want something that fires or not, okay? So there needs to be some kind of limit, some kind of threshold that says, when does the neuron fire or not? So this is why we add the activation function at the output of each neuron. And over time, a number of functions have been used. These days, ReLU is the popular one. And as you can see here, it's nonlinear, right? If the input value to ReLU, okay, so if that u value here is negative, then the neuron will output 0. And if the input to the activation function is positive, then the neuron will output that same value. And it could be a very, very large value, okay? So this is really what we want, right? Nothing happens until a certain point, and then we output a value, and this could be a really large value, okay? So if the neuron is stimulated enough, it can actually output very large values. And this is what we want, and this is how we introduce that nonlinear behavior in the neuron, okay? So obviously, a neuron by itself doesn't do much. They become interesting when we combine them into layers and networks. And this is probably the simplest one you could build. Okay? So we have an input layer where we will actually put our data samples to predict. We have an output layer where we will read results, right? We will read the predictions. And in the middle, we have a hidden layer, at least one. So in this case, just one. As you can see, it's fully connected, right? So all neurons are fully connected to the inputs, fully connected to the outputs, okay? That's why they're called fully connected networks, okay? So let's say we already trained this thing, okay? We'll talk about training in a few minutes, but let's say it's already trained. How would we use it, okay? So, of course, we need data samples. And for this discussion, let's say we're trying to classify pictures, okay? So we have a number of pictures, let's say animals, right? Dogs, cats, elephants, tigers, anything that you want. And we know what they are, okay? So we're going to take each image, we're going to flatten it into a vector, and we're going to store the pixel values in a matrix like that, okay? So this is the first picture, this is the second picture, and so on and so on, okay? So each picture has been transformed into a vector of pixel values, okay? And we know what those pictures are, okay? So we know, for example, that the first picture here is a category 2, and maybe category 2 are dogs, right? And we know the second picture is category 0, maybe that's cats, and so on and so on, okay? And let's say we have 10 categories in total. So that's the data set, okay? A number of pictures that we flatten into vectors and that we label with category numbers from 0 to 9, let's say, okay? Actually, we don't like using this. If you already work with machine learning, you know we don't like categorical values to be handled like this. We use another technique called one-hot encoding, okay? And that's a complicated word for a simple thing. One-hot encoding means instead of using category numbers, you're going to build a vector of bits, okay? And again, let's say we have 10 categories here. So we will have 10 bits, and we'll flip to 1 the bit that corresponds to the right category, okay? So if this one is category 2, then bit 0, 1, 2 is flipped, okay? This one is category 0, so we flip bit 0, and so on, okay? And why is this important? Because, well, this form, right, is actually much more expressive than this, because here we can see how many classes we have, first. And second, we could look at those numbers as probabilities for each of the classes, okay? And what this really says here is this sample has a 100% chance of being category 2 and 0% chance of being any other category, right? We know for sure because we know what the data set looks like, okay? Same thing here. We know that this last sample here is category 4, so it has a 100% chance of being category 4 and 0% chance of being anything else. Okay, and this is actually what we will get on the output layer when we put those samples on the input layer here, right? And we run those multiply and accumulates and those activation functions, etc. What we will read here in those neurons are the probabilities for the samples. Okay, so hopefully if we train our network right, okay, we would get to something like this. We take a data sample, and as you guessed, we need as many neurons in the input layer as we have features. Okay, so if we have 1,000 pixels here, we'll need 1,000 neurons here. Okay, then we run what is called forward propagation, so running that sample through the model, multiply, accumulate, activate, etc. And you read some results on the output layer. And again, if you have 10 classes, you will need 10 neurons on the output layer, okay? And you will read the probabilities for each class. So in a perfect world, this is what we would see, right? We would really see zeros everywhere except a 1 in the neuron that corresponds to the right class, to the right category. But nothing is perfect, and it's not going to happen like that. Anyway. What we care about is accuracy, so being able to successfully predict the maximum number of samples. Okay, this is what we're going to measure and track. Okay, so this is where we want to get. But of course, initially, the network is not trained. Okay, so all the weights corresponding to all those connections here, right? All those parameters, they have random values. So if you take a data sample and forward propagate, you get something completely wrong on the output layer. And it would not be something like this, actually. It would not be a 1 in the wrong place and zeros. It would just be random probabilities for the 10 classes, okay? Because again, the network has not been trained. So if we see this neural network as a function and we take a sample and compute the output, we're not going to get the right output. We're not going to get the right label. The right probability vector. We're going to get something different. Okay, let's call it y prime 1. So obviously, you need to measure the difference between what you expected and what you really got, okay? And we do this using a math function called a loss function. And remember that y1 and y prime 1 are really vectors, okay? Probability vectors. So it's not as easy as subtracting one from the other. But you don't have to worry about those because all the deep learning libraries provide those loss functions already. So you can just use one that matches the problem you're trying to solve, okay? So this loss function will give us the error, okay? Just a numerical value measuring the error, the distance, so to speak, between the two vectors. So actually, we're not going to do this sample by sample, okay? Imagine you have 10 million samples in the data set. It takes too much time to process every single one and train on every single one. So we actually train on batches of samples. Okay, so we're going to take 32 samples, 64 samples at a time, run them one by one through the model, and compute the total error for the batch. Okay, and then we're going to make decisions on how to reduce the error. Okay, more on this in a minute. Okay, so keep in your mind, we train on batches of samples, not individual samples. Okay. So, in a nutshell, the purpose of the training process is really only one thing. It's to minimize loss, okay, minimize prediction error for the data set by training over and over, right, iteratively, and by adjusting the weights gradually during the training process, okay? So what we're really trying to do here is, in these examples, I don't know how many weights we have, maybe let's say 25 or something like that, okay? We're trying to find the set of weights, the set of parameters that give us the highest accuracy for that data set, and that means the lowest possible error for that data set, okay? And we start from random weights, and we have to try to go as close as possible to that optimal set of weights, okay? And that's a difficult problem because you cannot compute them, right? It's not something, it's not an equation you can solve, so you have to gradually discover what those weights should be, okay? More on this in a second. So the training process really looks like this. We have a data set. Like I said, we slice it in batches, and again, we'll see in the code that deep learning libraries do this automatically, so no work needed. And we take one batch, okay? Let's say it's 32 samples. And we run each one of those samples into the network, okay? And we get to a prediction, and we compare the prediction to the actual result we were expecting, and we compute loss, okay? And we do this for all the batch samples, and we add up all the errors into the batch error, okay? So now we have a batch error that tells us, you know, what's the mistake, how big is the mistake we made for this batch. Okay, and now we can take decisions on how to reduce it. And this is done with an algorithm called backpropagation. And it's a scary one. It usually that's usually when people stop looking and stop studying deep learning because they want to understand backpropagation in detail, and it's a bit scary. Okay, so backpropagation, as the name implies, will go back from the output layer to the front. Okay, and layer by layer and neuron by neuron, it's going to adjust the weights in the direction that we know reduces error. Okay, so for example here, okay, this neuron, the error value that you get for this neuron depends on 3 parameters. Okay, so for these 3 parameters, you have to figure out if each of them should be increased or decreased to lower error, right? Or remember, these are floating point values, so these are the only 2 choices that you have, right? You can increase them a bit or decrease them a bit. So how do you know? Okay, I will answer that in a second. So once you've done that here, okay, you've updated those weights, so you can compute the new error for the next layer, and then you do it again. So the error that you get here for this individual neuron depends on 1, 2, 3, 4, 5 parameters, okay? So once again, here, you need to make 5 individual decisions on increasing or decreasing those weights. And you do this for every single neuron, and then you move back to the previous layer until you get to the input. Okay, that's why it's called backpropagation, okay? So now, obviously, you want to do this all over again for the next batch, right? Compute the batch error, backpropagate, and you do this again and again and again and again, okay, until you get to the end of the data set, okay? And this is called an epoch. And typically, you're going to train for 50, 100, 200 epochs. Okay, so it's really an iterative process. And you train and you predict again and again and again and again, right? Computing the batch error and then adjusting the weights in a direction that you know will reduce error. And you do this until you hopefully get to the right level of accuracy that you were expecting. Okay, so that's the big picture. Okay, and at the end of that process, you get to a trained neural network, okay? And as you can see, we have a number of parameters that are really important. The batch size is important. If you have very tiny batches, you backpropagate a lot, takes a lot of time. So yes, you will probably get to the right spot, but it takes too long. If you have a very large batch size, then you get less opportunities to run backpropagation per epoch, so maybe that's a problem too. The learning rate will actually decide on the size of the updates that you make to the weights. Okay, we'll talk about that in a minute. So it's important as well. Small learning rate, small updates to the weight. Large learning rate, large update to the weights. Okay, and again, too small will be a problem, too large will be a problem. And the number of epochs is how many times you go through the data set. These are called hyperparameters, and if you don't get them right, you will have lots of problems training. Okay. So that's the big picture. Okay. It's not really complicated. The only weird thing is, yeah, I get the batch size, the batch thing, and I get the backpropagation, but then you said we need to adjust the weights, each weight actually, in the direction that we know reduces error. How do we know? Right? How do we know if a given weight should be increased or decreased? Okay, let's look at a real example. So imagine you have a function here. Let's call it f, and it has two parameters. Okay? And the output is, let's call it z. Okay? And let's say that x and y are parameters and z is the error. Okay? And we start with random values of x and y, and we want to figure out what x and y should be to get the smallest value of z. Okay? That's really what we're trying to do. Find the set of parameters that give us the smallest possible output. Okay? And if we plot that function, let's say it looks like this. Okay? And remember, x and y are initially random, so we're going to start anywhere here. Okay? So let's say we start here. Okay? And let's say this is x and this is y. All right? So we want to get to the smallest possible value of z. So probably that's here, right? So in a way, we're going to walk down that slope until the lowest point in the valley, right? We're trying to get down to the valley. And remember, we cannot compute x and y. Okay, we have to discover them. So how would you do that, right? If you were in a mountain, how would you do that? Imagine you're in the fog, you see nothing, and you have to decide if you, if you should go forward or backward, and if you should go left or right. Okay, so what you would do is maybe, you would, with your foot, you would try in this direction and say, yeah, okay, this is down, all right, fine. And then you would go right and say, oh no, this is up. Oh, this is down. Okay, so this is down, this is down. So I'm going to take a small step here, and I'm a little lower than I was before. Okay, and you do this again and again and again and again, right? And if there's not a big crack, if it's a smooth surface like this, if it's friendly, you will actually get to the lowest point, iteratively by taking small steps in the right direction. Okay, that's the intuition. Now, obviously, deep learning doesn't have intuition, it's math. So how do you know for sure that you need to maybe increase x a bit, okay? Or actually here it would be, if the origin is here, okay, x and y, actually we have to decrease x and y a little bit to go down, right, initially. So how would we know? Well, remember high school? That's the part you're going to hate, by the way. So get ready to hate it. Remember high school, right? Remember slopes and remember derivatives, right? No, all right. You're too kind. Right. Well, that's exactly what we do here. Okay? This is a function, okay? Yes, it has two parameters, but we can compute the partial derivative for x, and we can compute the partial derivative for y at this specific point, okay? And so that gives me the slope in the x direction, and that gives me the slope in the y direction. And then if I have the slope, I know which way is up and which way is down, okay? Simple. So once I know that, well, I should decrease x a bit to go down in the x direction, and I should decrease y a bit in the y direction, then fine, I'm just going to do that. I'm just going to modify x and y just a bit in the right direction, and I get, let's say here, okay? And I do it again, and again, and again, and again, okay? And this algorithm is called stochastic gradient descent, or SGD. It's the granddaddy of optimizing functions. It dates back to 1951, okay, so it's nothing new. It has actually nothing to do with machine learning. It's a math optimization function. And that's the one that is still heavily used in deep learning, okay? So coming back to my example here, this is what actually will happen during the training process when you run backpropagation, okay? The library that you're using will compute the derivative for each of those three weights, okay, with respect to the error, and then decide if they should be increased or decreased. Do that, and then move on to the previous layer and do it again and again and again, okay? And this is how you know in which direction all those weights should be updated. And since we're taking small steps, we need to do it again and again and again, right? And this is why we do batch training, and this is why we need many epochs, because we take very tiny steps. But if we take tiny steps always in the right direction, right, eventually we get to the right place. Okay? That's all there is to it, right? High school math. Nothing to worry about. So obviously the surface is not going to look like this, right? It would be too easy. It could look like this, right? Or you could be seeing things like this, where, yes, you see them to have a nice global or, you know, a lower minimum here, and you have, you know, not as good ones here. So maybe you could start, you know, on the mountain here and walk down, and maybe you could fall in this hole here or this one, right? And let's say this one gives you a higher error than this one does. So it's probably more desirable to be here than to be here, right? And they're called local minima. And another problem could be saddle points. And this one is actually even worse. So it's like a horse saddle. And in this direction, right, we can see, yes, this point here, the green point here, is actually the minimum, so fine. But in the other direction, right, like this point here is actually a maximum, right? And if you remember high school again, you know that the derivative is equal to 0 when a point is a minimum or a maximum, okay? So if we actually started here and went down exactly to that green point, we'd be in trouble because derivatives would be 0. We could not update the weights, okay? So saddle points are actually a problem too. So it's a long-lasting debate in the deep learning community on whether these things really exist, whether they really are a problem, do we really meet them in our daily experiments, etc. And this reference article from 2015 says pretty much yes, okay, these things exist, okay? And keep in mind here we have only 2 parameters, 2 dimensions, but state-of-the-art models, they can have millions, tens of millions of parameters, okay? So you have to try to visualize this in 10 million dimensions, okay? If you can actually do that, welcome to Earth, right? Please solve all our problems, okay? So chances are you cannot, okay? And I can't either. So that's why intuition is really important. So yes, it's quite likely that we have weird things like local minima and saddle points, but what Ian Goodfellow says is, yes, they're here, but they don't really impede the training process, right? By some magic we don't quite understand, we actually manage to go around them or escape them. So, you know, don't lose too much sleep about those anyway, right? That's the #1 question I get. Yeah, but deep learning is just, it's all crap because of local minima. It's like, yeah, okay. In theory, yes, there is a problem. In practice, it doesn't really bother us, okay? If you want to read that one, you'll get more information, okay? So that's for the training process, right? So we do that again and again and again. And how do we know that we're actually making progress? Well, we keep part of the data set. We call this the validation data set, okay? And it's very typical to do this in machine learning. You split your data set between training, validation. And periodically, so at the end of each epoch, we run the validation data set through the model in training, right? This should really say in training neural network, not trained, because it's not finished. We're still training, okay? And we measure the prediction accuracy for this data set. And this gives us a sense of how well or how bad the network does on samples that it hasn't seen so far, okay? Because remember, these samples are different from the training set, okay? So we're going to do that. We're going to see this at the end of each epoch, and hopefully it goes up, showing that not only is the network learning, it's also learning to predict samples it has never seen. And at the very end, once we're done, right, once we're completely done with training, we're done tweaking, and we want to compare this model to the previous models that we trained last month, last year, etc. We want some kind of benchmark. We're going to use a test data set, okay, so a third data set, that gives us just, again, a benchmark accuracy for that model. Okay, so it's a very typical way of doing things, 3 data sets. Okay. So if we plot all those things, it should look like this. So we should see training accuracy going up really quick, and then plateauing, if that's a word. And if we train long enough, we get to 100% accuracy, okay, guaranteed. If the network is deep enough, large enough, if you train long enough, if you have enough data, you always get to 100%, okay. So the loss function, the error, right, the prediction error obviously goes down almost to 0. If you plot the validation accuracy, it's possible you see something like this, okay? So again, it goes up. It tends to follow the training accuracy and plateaus. And you might get, you know, a high value here, like a small bump here, and then plateaus again, and then it drops. And it never, never recovers, okay? It's quite possible this is really more, you know, more jittery than this. It could be like this, right? Very, very jittery. But then at some point it drops and never recovers. And that's extremely bad, okay? This is called overfitting. It's the #1 problem in machine learning. And what overfitting really says is you train so hard on the training set that it's the only thing you can predict. Okay, so the model is specialized in predicting the training data set. It cannot do anything else, okay? So that's really bad because obviously in real life, you don't want to predict the training set, you want to predict real life samples, right? And these will come from, you know, the validation accuracy anyway. So this means that when you're training, you should really plot this. You should keep an eye on the training accuracy, of course, but you should also keep an eye on validation accuracy. And you should plot this thing at the end of training and decide which one is the best epoch, right? Which version of the network should you actually use for prediction, okay? And you cannot know in advance. So in order to do this, what you really do is save, at the end of each epoch, you save the weights, right? You save the version of the model at the end of this epoch. And then you plot, and you say, oh, okay, I trained for maybe 200 epochs, but the best one is actually 129, and that's the one I'm using. Okay, so you have to save the weights, all the weights at the end of each epoch to know which one you're going to use in the end. Okay? So to sum things up, deep learning is really about finding a minimum, right? You don't care about finding the minimum. You'll never know if you found it. It's a NP hard problem. So there you go. So all you need to find is a minimum that's good enough, right, to give you the accuracy that you need for your business problem. Okay, if your business problem requires 95% accuracy, then fine, right? Do that. No point in chasing 97% for weeks and weeks and weeks, maybe you'll never get there. So you need to decide what accuracy you need to solve your business problem, and once you get there, good, okay? And of course, you need to find it fast, because if you were able to find it fast, if you can actually learn quicker, then you train for shorter periods of time, you can iterate more, you can save money on training, etc., etc. And if you can find it reliably, if it's not just a lucky accident, if you can find it again and again and again, it's very good, because again, you will train many models. You will try many combinations. You will try different data sets. You will try different hyperparameters. You will retrain periodically, etc. So you need to be able to hit this accuracy level again and again and again. If you just hit it once and then have trouble hitting it again, then it's not a viable solution. So let's look at a first example. Yes, that's the one. Okay, I guess that's large enough. So I'm going to use a deep learning library called Apache MXNet, which is the favorite library at AWS. And we're going to try to classify a data set called MNIST, which I'm sure you've seen before. It's a nice toy data set. It's not good for anything, except experimenting. Okay, so this is MNIST, right, over there. So 70,000 digits, handwritten digits, so 0 to 9. And obviously the game is to learn to classify those images in the right category. Okay, and they're black and white images, 28 by 28 pixels. So the first thing I'm going to do is download the data set that is already split in training and validation. I'm going to import MXNet. I want to train for 50 epochs. I'm going to use an iterator to load the data set from the files. Okay, and the iterator will slice that data set into batches automatically for me. Okay, so I don't have to slice it into pieces and pass that to the model. The iterator does it automatically for me. And then we build the network. And this is almost, yeah, this is pretty much the one we saw on that slide, except it has 2 hidden layers. So I've got a first layer, which is the input layer. I call it data. I don't need to give it size. MXNet will figure it out automatically from the iterator. And if you remember that slide with the fully connected network, my input layer is flat. Okay, it needs a vector, right? It needs the data samples should be vectors. So I have to flatten my images. Okay, so I flatten the images into vectors, and then I have a fully connected layer with 1024 neurons activated by ReLU, and then I have a second fully connected layer with 512 neurons activated by ReLU. And then I have the output layer with 10 neurons because I've got 10 categories, right? 0 to 9. Okay? So those 6 or 7 lines are all I need to actually define my neural network. Okay? And it doesn't matter which library you use, you'll find something similar to this. You just stack the layers like this, you connect them, and obviously you never worry about connecting individual neurons. That would be painful. Okay? So now I've got a model. Okay? And I've got a data set in an iterator, and I have a model, so I need to put the two together. This is called binding here. Okay, so binding the model I just created to the training iterator and the validation iterator. And then I need to set an optimizer. Okay, so I could actually use SGD right here with a learning rate, a fixed learning rate like this. Why not? But there is a whole bunch. I said SGD was invented in 1951, so more interesting options have been invented since. Specifically, algos like ADA delta and so on that can actually modify the learning rate during the training process. Right. So if the slope is very steep, they can speed up, and if the slope is very flat, they will actually slow down and allow you to explore, okay? And that's what ADA means, adaptative, okay? So they will change the learning rate during the training process. Okay, and then I can train. So let's actually run this one. okay? And we can see the training process going on, okay? Whoops. So we see the epochs going by, and we see the batches going by, okay? And we see, you know, we actually have a training accuracy that gets to 1 very quickly because it's a large network, and it overfits pretty quickly. So you know, I've done this before in the interest of time, and I saved my model here, and I get to a validation accuracy of 98.13. It trains for a few minutes, but I don't want to waste a few minutes. Okay, so this is what I get, right? I trained for 50 epochs, that fully connected network on my data set, right? And I get to the validation accuracy of 98.13. So is this good? Is this bad? How do you know, right? Sounds good, okay, 98%. But you will not know until you try real-life samples. So I did what I had to do. I took my paintbrush application, and I drew some digits, right? And you can see them here. And we're going to try and predict them using the model that I just trained. So I can load that model again, okay, which is pretty much as easy as this, right? Load checkpoint with the name of the file storing all the weights. Okay, and then I can predict my digits. Okay, and predicting one of those images is very easy. You load the PNG file from disk. You turn it into a vector, right? You flatten the image into a vector, and you push it through the trained network. Okay, there's nothing to be worried about. That's really one line of code. Okay, load the image, put it in a vector, push it through the trained model, and then read the outputs. Okay, so very simple to predict. And when we do that, and let me run those cells again. I just want to make sure I have the right model here. Whoops. There we go. Run all the cells. Okay. And so for each of these pictures, we see a vector of 10 probabilities, right? This is exactly what we read on the output layer for the neural network, okay? So we see that 0 worked out, okay, because actually probability 0 is the highest, 99%, okay? And for the 1, probability 1 is the highest, etc., etc. So 2 is very good, 3 is very good. And you never really see zeros and ones. It's because I stop at 4 decimals. So this really means it's at least 0.9999 something, okay? You will always see non-null values here. 4 is fine, 5 is fine, 6, good, 7, 8, and 9. This should be the highest, right? It's not. This one is the highest. So 0, 1, 2, 3, 4. Okay, so my model is confused. It thinks this is a 4. Okay? So that's what I told you. You have to try different samples. You know, the validation data set is one thing, but the test data set, which should really be composed of real-life samples, stuff that people will really predict, not just sample data sets. This is really what tells you how well your network performs. So this is disappointing, right? Because I tried 10 and one of them is wrong. So why is that? So you could say, well, this is really a very ugly 9. So yeah, you know, you can't expect the model to predict ugly stuff like that. Okay, fair enough, but some people write really, really bad digits, so you should still be able to figure it out. But remember what we did to these images, right? We flattened them, okay? So intuitively, it doesn't sound like a really great idea because images are really 2D objects and we flatten them, so we lose the relationship, right, the proximity between some of the pixels. And probably that doesn't help understanding what's in those pictures. So to solve this, a different type of network was invented 20 years ago already, and they're called convolutional neural networks. And these networks are the kings of image processing, image classification, okay? And the basic idea here is will work with the 2D image, or maybe 3D if it's a color image, right? It's going to be 3D because it's red, green, blue, okay? But anyway, we don't flatten anything. We stick to multi-dimensional objects, and we use two operations. We use convolution, and we use pooling, also called subsampling, okay? So convolution is actually extracting features, okay? Here's an example. If you take this filter, 3 by 3, and you slide it across the image, right? So 9 pixels by 9 pixels, going all the way, applying the convolution operation, which is pretty much taking the underlying pixel here, multiplying it by the corresponding value in the kernel, okay? And you do this 9 times for the 9 pixels here, and you add everything together, and that becomes the new top left pixel. And then you slide, and you do it again and again and again, okay? If you use this filter, these specific values, you go from this image to this image, okay? So this is really an edge detector filter. And this, what did we achieve here? Well, we detected the edges in the original picture. And we threw away pretty much everything else. Everything else is black, right? We only kept the edges. So we extracted the edge feature in this image. Okay? And this is what convolution is about. So by running many different filters, okay, it could be 20, 30, 50 filters, you extract different features from the image. So it could be edges, it could be contrast, it could be vertical lines, horizontal lines, whatever, and you get a combination, a new set of convoluted images, which you then shrink with pooling. I'll show you how in a second. And then you do that again, okay? And you get to a collection of very tiny images that look nothing like the original image, but they kept the good stuff. They kept the features and the important information. And then you can flatten this and use a fully connected network, okay? That's the intuition behind convolution networks. You automatically extract features using a collection of filters, and then you throw away, you shrink the images, you throw away the useless information in those pictures, and you do that again and again and again. And if you heard that deep learning extract features automatically, this is it, okay? This is what people mean. You use kernels or filters to extract important information and throw away the rest. And obviously, we have no idea what those values should be, right? Here it's just it's an example, but initially, the values for all the features generating those pictures are random. So they are learned during the training process. So the training process of a convolutional neural network is really about finding which filters extract the right features to help you understand those images, right? And it's the exact same process. Backpropagation, SGD, etc., etc. Okay? So it gets a little more complicated, but the overall picture is the same. Okay? You learn the filters that lets you extract the right features. Okay? Pooling is much simpler. Pooling is just about, if we do a 2 by 2 pooling here, we just take 2 by 2 pixel blocks and we keep the brightest, right? The brightest pixel, the highest value. Okay? And if we do this all over the picture, then we get a smaller picture. And the intuition here is that in this image, you don't care about the black stuff. Okay? You want to throw that away. It tells you nothing. It was filtered out. Okay? What's important is really the white pixels, the edge of that weird beast. Okay? So you can shrink the image by keeping the white pixels, and it will gradually distort the image, obviously, but you keep enough information to learn to classify them. That's the idea. So let's really quickly try this. So we're going to try to classify the same data set, but this time with a convolution network, and it's pretty much the one you saw on the slide, right? Input layer, convolution with 32 filters, pooling, 2 by 2 pooling, convolution again with 64 filters, pooling again, 2 by 2, right? So here from the initial image, we built 32. And then from the 32, we build 64, okay? And we shrink them. So we end up having a large collection of tiny images, and we flatten everything at the end. So all those tiny images become one big vector, and we use a fully connected layer to classify them into 10 categories, because once again, 0 to 9, okay? So you see this API is quite simple. You can literally look at the network and code it, right? Just stack the layers, and there you go. And the rest is the same, right? We bind, we train. So I trained again in the interest of time, takes again 2-3 minutes. And we get to 99.15 accuracy this time, okay? So it's a bit higher than the previous one, but now we're suspicious, so we're gonna try that new model, the one that we saved, and we're going to predict again. So 0, 1, 2, 3, they all look very good. 6, 7, 8. What about 9? So, is this the highest now? Yes, it's the highest. It's still not great, right? Which is a tribute to my ugly 9 here. It's still not great, but it's the highest. Okay, so if I had to decide which thing is this, then I would say, okay, it's a 9. Not super sure about it, but okay. If I have to make a guess, I'll tell you it's a 9. Okay, and obviously, you could keep tweaking this to get better results. You could have more filters, more layers, etc., etc. But again, the intuition is really important. Okay, that's why CNNs work really well on images. It's because they keep the 2D or the 3D image, and they don't flatten stuff. Okay, they just extract features from the actual image. So it makes sense that they would be able to classify them better. So you can do all kinds of crazy stuff with this. There's an extra API in MXNet called Gluon, and specifically gluoncv, which means computer vision, that provides you with a collection of pre-trained models. Okay, and these are state-of-the-art models with hundreds of layers. They've been trained on really big data sets, and you can do classification, detection, segmentation. Right? These are just a few examples. And any of those is literally 5 lines of code. So I'm just going to show you one, but you'll find everything on GitHub. Let's look maybe at, let's look at, okay, classification. Okay, so how complicated is it to do this? So we're going to call this API to load a pre-trained model. Okay, so it's called a model zoo. So we fetch a pre-trained model from the web, already trained, so no training needed. We load a local image. We're going to normalize it. Okay, normalization is important. So make sure the the red, green, and blue channels, etc., are normalized. And then we predict it. So we take that image, push it through the trained model, and then we can read the results, and that's it. Okay. So training your own model is fine, and we could run one of those. Yeah, let's try. Okay, let's try this one. Okay, let's try to segment this. Here we go. Okay. Okay, so that's the original picture, and I'm running it on my Mac, so no GPU, so it takes a few seconds. But here you take an existing model, pre-trained, and you just get the job done, right? So, of course, you could train that model on your own data set, right? There you go. 5-6 seconds, no GPU. So on a GPU, it would be just like this. And this really takes 5 lines of code, okay? So before you go and try to build everything from scratch, just consider existing models, pre-trained models that might be good enough to do the job, right? And you would save an insane amount of time by using those pre-trained models. Okay. Very last thing I want to talk about is we looked at fully connected networks and we looked at convolution networks. Okay, and if we predicted with those, if we took 100 samples and predicted them in any order, we would still get the same results. Okay, sequence doesn't matter. which is a problem because when you want to work with time series, when you want to work with sequences of data, the order of the samples does matter, right? When we're translating, for example, we don't translate each word independently. We'd look at the previous words to actually get some context. So we need some kind of memory, short-term memory on the past few predictions to make the right prediction. And this is what LSTM networks are all about. So they have a different type of neuron, which I will not explain. I don't have time, and it's a little more involved. But you just need to remember that a prediction done by an LSTM neuron depends on the input, and it depends also on the past few predictions. So they have some kind of memory, right? That's why they're called short-term memory networks. And this is very good if you want to predict sequences, right? So time series, machine translation, Bitcoin prices, anything you want. And talking about machine translation, we have an open source project called Sockeye that you'll find on GitHub that uses an LSTM architecture to let you train machine learning models for machine translation, okay? And it's super simple to use. And maybe we can do a really quick demo if I still have a, come on. I still have an SSH connection here. So I took a data set for German to English. And no. Oh, yeah. Slow connection, but we'll find. OK, so I have a few million sentences in English and in German and English, and I trained a model from German to English. It took a few hours on a couple of GPUs. So I could take some German sentences here, and I could run them through that. And I have just one for you here. Hopefully that works. Yeah, OK, see? So if you want to build your own translation model, just go grab Sockeye, train for a few hours. If you have the data set, it's not complicated. It's a pre-existing architecture, and you can just do it like that. OK, so you can build your own translation service, just like that. OK. All right. I'm out of time, so. OK, I'll take 30 seconds for the crazy stuff, because I hate not talking about it, and then I'm done. So the last type of architecture I want to talk about is called Gans, Generative Adversarial Networks. And they are weird, right? So who knows who these people are? I know you're working hard, but you got to watch movies, right? Come on, TV or something. No one? No one knows. I had nothing to win, but OK, if I had something to win, I would give it away. No? No. That's your last word? OK, now no, you're just very suspicious now, right? Of this Frenchman showing you weird stuff. OK, you're right to be suspicious because these people do not exist, right? They are generated faces. And they're not copy-paste, right? So it's not the nose of Brad Pitt and the ears of Johnny Depp or something like that. It's really generated pixel by pixel by looking at a large number of images in the celebrity data set. That's why they end up being quite good looking. The network learns to generate similar samples, okay? But these are completely fake, right? Here's another example. You remember that, right? When you were 5-year-old, or if you have kids, you have stuff like this on your fridge, right? I'm sure, I do. So these are cars, right? This is the road, these are trees, etc. And this is called a semantic map, okay? And again, you can, by training a neural network on images and the corresponding semantic map, you can then predict this semantic map, okay? So you give this to the model, and the model will generate the actual picture, okay? And this is HD, right? Now, these are HD pictures, so you can zoom in, and you can see a lot of detail, actually, right? These are really, really precise, okay? So this GAN area of research is moving all the time. It's really crazy, and if you're interested, you know, I would suggest you read about that. You'll see some even crazier applications of GANs, right? Generating a new reality. All right, so how do you get started with all of this? Well, I would recommend, obviously, taking a look at the AWS website. where you will find information on all the tools and all the libraries that our customers use to build pretty cool stuff. Okay, the blog has some technical articles, etc. If you're curious about MXNet and Gluon, it's all on GitHub, right? So just go and grab the sources, grab the tutorials. There's lots of documentation for it, and you can replay a lot of those examples. If you're already doing machine learning in production and you have scaling problems, right? We have a service called SageMaker that lets you train pretty much anything. TensorFlow, MXNet, PyTorch, scikit-learn. We have some built-in algos as well to save you more time. So if you just want to focus on machine learning and not on infrastructure, I would recommend taking a look at SageMaker. We have SDKs, and we have a very, very cool integration with Spark. If you use Spark, SageMaker makes a lot of sense as well. And finally, here's my blog on Medium, where you'll find lots of articles on machine learning, deep learning, SageMaker, and more crazy stuff. By now, I've got quite a collection of talks on YouTube as well. So if you want to dive deeper on those topics or explore what AWS has to offer, you'll find something here. And the code that I use today and much more is available on GitLab. So just go and grab that, and you can run these examples and more. All right? Okay, I'm done. Thank you very much. If you want to stay in touch, thank you.